All right, chapter 20, 20.1, we're going to deal with electrochemistry, and this has to do with kind of the transfer of electrons in chemical reactions. In section 20.1, we're going to deal with one type of thing, and we're going to talk about ox-redox reactions, or what we call oxidation reduction reactions. So, in chemistry, or in when we have electrochemical reactions, electrons are transferred from one species to another. And these are called oxidation reactions, or what's called oxidation reduction, or ox-redox reactions. And in each of these reactions, we need to assign oxidation numbers to each element to show what is being oxidized and what is being reduced. So, you can see here we have the following reaction: zinc solid plus 2 hydrogen ions yield zinc as zinc ion with hydrogen gas. We have assigned oxidation numbers to each of those elements or ions, and we're going to explain here in a couple slides why they have the particular number with them. But for the meantime, what I want to focus on is what is being oxidized and what is being reduced. Anytime something is oxidized, it loses electrons. The easiest way to remember that is O, oxidized has an O, loses has an O. So when it's oxidized, you're losing an electron. So if we look at zinc here, zinc goes from a oxidation number of 0 to +2. That means it's losing electrons because it's gaining a positive charge. So when it's losing electrons, it's getting oxidized. Likewise, if something is reduced, it's going to be gaining electrons. So we look at hydrogen here. Our hydrogen species has a charge of +1, an oxidation number of +1, and it goes to 0, which means it's gaining electrons or it's gaining a negative charge. So that is our oxidation reduction reaction. Now, here is when they flip-flop. When something is reduced, it's called the oxidizing agent. When something is oxidized, it's called the reducing agent. So here we look at zinc. Zinc is being oxidized because it is losing electrons. Therefore, zinc is the reducing agent. And hydrogen, since it is gaining those electrons or is being reduced, is called our oxidizing agent. They kind of flip-flop. It's very similar to kind of acid conjugate base, base conjugate acid that we've talked about in the previous chapters. All right. What we're going to focus on when we talk about ox-redox reactions now is assigning oxidation numbers and then writing the actual equation for an oxidation reduction reaction. So there are some general rules here when we assign oxidation numbers. First, number 1, elements in their elemental form have an oxidation number of 0. So neon, 0. Iron, 0. In their elemental form. That would be solid, not as an aqueous solution. Keep that in mind, not as an ion, but as a solid. Also, all your diatomic molecules, your halogens, nitrogen, oxygen, hydrogen, when they exist elementally, they have an oxidation number of 0. Number 2, the oxidation number of monatomic ions is the same as its charge. So for example, if we have iron as an ion, it's either going to be +2 or +3. If we have chlorine as an ion, it's going to be -1. If we have calcium as an ion, it'll be +2. Just a couple of examples there giving oxidation numbers. Number 3, nonmetals tend to have negative oxidation numbers, although they can certainly be positive sometimes. Oxygen has an oxidation number of -2, which is what it would what its charge would be typically, except when it's in the peroxide ion, and then it has an oxidation number of -1. Remember, peroxide, the formula for peroxide is H2O2. Also, hydrogen is -1 when it's bonded to a metal and +1 when bonded to a nonmetal. So oxygen and hydrogen kind of have a couple exceptions to their rule when we talk about nonmetals. Continuing with nonmetals, fluorine always has an oxidation number of -1, and the other halogens typically have an oxidation of -1, when they are negative. They can have a positive oxidation number, and that usually exists when they are bonded to oxygen in oxyanions. Continuing with our oxidation sum, the sum of oxidation numbers in a neutral compound is 0. That seems to make sense. And number 5, the sum of oxidation numbers in a polyatomic ion is the charge of the polyatomic ion. So for example, phosphate is PO4 minus 3. The oxidation number of phosphate is minus 3. Sulfate, SO4. The oxidation number for sulfate is minus 2, since sulfate has a charge of minus 2. So now that we've covered oxidation numbers, let's look at the ways in which we have to balance oxidation reduction reactions. Now, we're going to add a couple things to how you've balanced reactions in the past. And so this is continuing to work on balancing equations that we've worked with, but we're going to add a couple things. So when we balance these oxidation reduction reactions, this is simply a way on paper for us to account for the electrons that are moving from one side of the equation to the other, or what's being oxidized and what's being reduced. So typically what we do is we're going to do the half method reaction, which we're going to take half of the reaction at a time. So we're going to assign oxidation numbers to determine what's being oxidized and what's being reduced. And then we're going to write the oxidation and reduction half reactions. And we're going to show an example of this in a second. Once you've balanced each half reaction, you're going to have to balance each half reaction. And how you're going to do that is a little differently than what you've done in the past. You're going to balance elements other than hydrogen and oxygen. So you're going to leave hydrogen and oxygen alone. You're going to balance oxygen by adding water. You're going to balance hydrogen by adding H+. Then you're going to balance any other additional charges by adding electrons. You're going to multiply the half reaction by the integer so that the electrons gained or lost are the same. You have to have the electrons lost and the electrons gained be the same. You're going to add the half reactions together, subtracting the things or canceling out the things that appear on both sides. You're going to make sure the equation is balanced according to mass, and then you have to make sure the equation is balanced according to charge. So what the heck does this process look like? Well, let's go through this process step by step that we just got done talking about. We have a reaction between manganese oxide, that's permanganate, MnO4, and C2O4 minus 2. Here's our reaction. We have MnO4 minus plus C2O4 minus 2. Now, real quickly, which one of these is being oxidized and which one's being reduced? Well, let's go ahead and let's assign oxidation numbers to each compound. Right. Real quickly here, oxygen has a charge of minus 2, which means it's minus 8. Manganese then therefore has to be plus 7 because the entire compound has a charge of minus 1. Same thing over here with oxygen. We have our C2O4. O4 is minus 8 since oxygen's minus 2. Since the charge of the entire thing is minus 2, that means all our carbons total have to be plus 6. Since I have 2 of them, it has a charge of plus 3. In solution, manganese is plus 2 as an ion. It'll be plus 2. Then we have a neutral compound here. So on this carbon, we have two oxygens with a charge of minus 4, since each one's minus 2. Therefore, carbon has to be plus 4. So what you have here is manganese is going from plus 7 to plus 2. So it's being reduced. It's gaining electrons. And carbon's going from plus 3 to plus 4. So it is oxidizing. So now we're going to take the half reactions. We're going to focus on just MnO4 going to Mn, and C2O4 going to CO2. So here's what this looks like. C2O4 going to CO2. To balance the carbon, we're going to add the 2 coefficient out in front. So now we have 2 carbons and 2 carbons. After that, however, on the left side here, we have a charge of minus 2. To make sure we have that charge of minus 2, we have to add 2 electrons on the right-hand side. That one's good. That one's taken care of. Next up, if we look at MnO4 going to Mn plus 2, Our MNs are balanced. All right. The next thing that we need to do is balance our oxygens. When we balance our oxygens, we're going to have to add 4 waters. Remember, when we add in electrochemistry, when we balance our oxygens, we add water. So we have 4 oxygens here. We're going to add 4 waters to the equation. Next up, right, we have to make sure our hydrogens are balanced. Now we've added hydrogens into the equation. So we have 8 hydrogens over here. We're going to add 8 hydrogens on the left-hand side. Last thing that we need to be concerned about is our electrons. We have 1 electron over here. We have 1 electron over here. Actually, let's look at our total charge here. Let's go back and look at our total charge. Our charge is +2 on the right-hand side, which means it needs to be +2 on the left-hand side. How are we going to balance that out? Well, we have a charge of +8 with our newly added 8 hydrogens. We have a charge of -1 with our MnO4. So I'm going to have to add 5 electrons. When I add 5 electrons, the left-hand side has a charge of +2. The right-hand side has a charge of +2. So we've balanced our elements other than carbon, or excuse me, we've balanced our elements other than oxygen and hydrogen on both half reactions. We've balanced our charges, we've balanced our oxygens, we've balanced our hydrogens. Now what do? Well, now we have 2 reactions here. We're going to put together our 2 half reactions, and what is this going to look like? Well, we need to have the same number of electrons on each side of the equation. We have 5 electrons over here. We have 2 electrons over here. So what we're going to have to do is we're going to have to multiply the first reaction by 5 so we can get 10 electrons, and the second reaction by 2 to get 10 electrons. So when we do that, we multiply our top equation by 5. We multiply our bottom equation by 2. We have 10 electrons and 10 electrons. When we add these equations together, we get our 10 electrons, we get all our reactants added together, and all of our products added together. Now what we can do is we can cancel out the things that we can cancel out. So what can we cancel out? We can cancel out our 10 electrons on each side because those cancel out. And we're left with 16 hydrogens plus 2 MnO4 plus 5 C2O4 gives us 2 Mn plus 2, 8 waters, and 10 carbon dioxides. That is basically how you're going to do a net or a ox-redox reaction. Lastly, if we were balancing in a basic solution, a couple things here. If the reaction occurs in a basic solution, you can balance it as if it occurred in an acid. Once the equation is balanced, adding OH to neutralize the H to create water in its place. If this produces water on both sides, you can subtract water from both sides. And we'll do a couple examples of that in class. But in general, that's a great example of doing ox-redox reactions, applying your oxidation numbers, breaking into half equations, and solving your ox-redox reaction.